Okay. Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explorer Alliance. And here we are with yet another Astronomical League Live. The host of this program is Terry Mann. Terry's on with us right now. Terry, thanks for bringing this whole program together. And we have, you brought none other than Lou Mayo here. So this is wonderful.
Thank you. It is. I am so happy to have Lou Mayo and David Levy and John Goss here tonight. You just don't get a better lineup than that. So why don't we go ahead? Unfortunately, Carol couldn't be here tonight. He had some previous engagement that he had to be at. So he will join us, I'm sure, again. For those of you who don't know, this was Carol's last year as president of the league. And so he will not be president of the league because he cannot run again. So Chuck Allen will be president effective September 1st.
Oh.
So, but I'm sure he'll be back on AL Live along with Chuck. We'll have the whole gang here probably.
And so, who will be vice president? Who will be vice president?
Thank you. Yes, I will be vice president starting September 1st. So yeah, and I'm very honored to be that. You know, it's a great organization. If anybody takes time to really look, everybody does amazing things, and it's all volunteer. So I am proud of everybody and everything that the league does. So it makes it a real joy to be here. So thank you. Now let's kick this off with David Levy, and I want to say something about David before we start. He gave one of the most inspiring talks at Linda Hall Library. I sit there in total amazement. He was perfect. He was so energetic, so spot on with everything. I loved every second of that talk. David, thank you very much for doing that.
Thank you very, very much for your comments. I'm really, really glad and relieved to hear them. I wanted to say that I'm especially excited today that we have Lou Mayo on. It's going to be, Lou is incapable of giving a boring presentation or writing a boring article or saying something that's not interesting. He is incapable, couldn't do it if he tried. But I'm really looking forward to what he has to say today. And I hope I'll get to see you in Tucson at some point, Lou. Anyway, for my quotation today, I'm going to go into the world of prose. It's from the book Jane Eyre by Charlotte Bronte. I don't know how many of you are familiar with the BBC 11-episode production of Jane Eyre, but Wendy and I were in the habit of watching it at least once a year. And now that I don't have Wendy, I still watch it at least once a year, which means I'm going to have to watch it again soon. The quotation I'm going to give today comes just after the scene where she is bumped into Rochester, who has fallen off his horse. And she's a little bit upset about that first meeting with him, and then walks back towards the gloomy house. And this is what it says in the book. I lingered at the gates. I lingered on the lawn. I paced backwards and forwards on the pavement. The shutters of the glass door were closed. I could not see into the interior, and both my eyes and spirits seemed drawn from the gloomy house, from the gray hollow filled with rayless cells, as it appeared to me, to that sky expanded before me, a blue sea absolved from taint of cloud, the moon ascending it in solemn march, her orb seeming to look up as she left the hilltops, from behind which she had come, far and farther below her, and aspired to the zenith, midnight dark, in its fathomless depths and measureless distance, and for those trembling stars that followed her course. They made my heart tremble. I'm sure familiar with those, though. My veins glow when I view them. Little things recall us to earth. The clock struck in the hall. That sufficed. I turned from the moon and the stars, opened a side door, and went in. Thank you, Terry, and back to you.
Thank you, David. That's beautiful. All right. Well, tonight we have another big surprise. We have John Goss on here, and you will be seeing John from time to time on AL Live, which mostly he is on AL Live quite a bit, but he's going to add kind of a new dimension to AL Live. He's going to kind of talk about a lot of what the league can do with the posts that are on Facebook and some of the other
Right.
things that he's discussed. So, John, I'm going to turn that over to you. Thank you for being here. I appreciate it.
Well, you're welcome. Thanks for having me. I was scheduled to be on here, and then I wasn't, and then I was. So here I am, and I appreciate you bearing with me in all this back and forth stuff. I'm going to have to screen share here, so I hope I have the ability to do so. Good. Yes, I'd like to talk about what the Astronomical League does on Facebook. You hear a lot about Facebook in the news and in our culture and society and all that, but yet I am surprised at the number of people who are not on Facebook. In a way, I'm surprised, because if I wasn't handling this bit of league operations, I wouldn't be on Facebook either. But anyway, a lot of people are and a lot of people aren't. So this is for the people who are on Facebook and who'd like to know a little bit more about what the league does on it. We also have a YouTube channel, which I will briefly touch on. So let's see what I can do with this. So what do we got on Facebook? Well, you can break it up into a lot of different categories, but we really have our monthly maps, suggestions on things to observe in the sky, interesting things in the sky, interesting astronomical news, and so on. These 4 graphics I have here represent kind of a summary of what we do. On the right-hand side, we have a September map. We have in the upper part, we have a little guide on how to complete the active galactic nuclei program. And we have special stuff like T Corona Borealis, which still hasn't exploded yet. We talked a little bit about that and how to find it and what it's all about. And plus, we have some awards which we like to mention as well. So I'd like to delve into this a little bit more. Our monthly maps. The September issue came out today, and we have them in English, as you can see, and also in Spanish. You're free to download these. You're free to make copies and hand them out to your friends, neighbors, club members. If you have outreach events, you can take them to that as well. Just delving into a little bit more about what they contain. Of course, we have stuff in the night sky, but we also have instructions on how to find your way around. So this is really meant for beginners. As you can see, in September, you start with what you know or what you can readily find, such as the Big Dipper, how to find the North Star, how to find Arcturus, how to find Spica, how to find Vega, and so on. So once you do these 5, 6, 7 steps, you will have covered the night sky pretty well, and your knowledge of what is up there grows quite a bit. As I said, this is meant for clubs and individuals to use. You're free to download it. So please go ahead and do so. We also, offer a monthly double star. This is for September, which is Eta Cassiopeiae. How to find it, kind of what you're going to see, how far apart these 2 stars are, that type thing. So really the idea behind this is to get you outside and looking up and trying to find these things. I don't choose the most difficult ones to find. I choose the ones which hopefully a beginner or a person who's interested in the subject can hopefully look at through a small, low-powered telescope, generally 50 magnification or less. I think I said Eta and I have beta there. Huh. I always make one mistake. Always make one mistake. But anyway, 30 power or more should do fine for this one. We also include a monthly activity. Again, to get you outside to look at the night sky. September, we have an eclipse, pretty meager eclipse as eclipses go, but that's what might make it more interesting than anything else, because it's not a big bite, big chunk taken out of the moon in the Earth's shadow. It's more like just a little nibble, and that'll be on the evening of the 17th, and it can be seen from most parts of the United States, if it's clear, if you're lucky. So we have a monthly activity like this. We also try to do other information, other activities, and try to have this posted every other day. So there's always something new for you to look at, such as, let's go back to June 25th. We have Beta Lyra, not double, it is a double star, but it's a variable star, what it's mostly known for. This shows you how to find it, what you're going to see, and what's causing what you're seeing. So it gives you kind of a primer of what eclipsing variable stars are like, and Beta Lyra is a very good example of that. On the right-hand side, we have Messier 8. Again, it's a little primer on what it's about, what you can see in a photograph, and what you can see through a really nice sketch. So, it identifies certain features of M8, what it's all about. It's a pretty interesting nebula. This time of year, it's especially beautiful in the southern sky shortly after sunset. We also try to include lunar information, lunar activities, one or so a month. Obviously, this is exploring Gassendi, a crater, fairly large crater, but it was well known. Well, it's not really that well known, but it was known by William Herschel, who thought he saw something really strange in there. So we pose it as a question, and the answer is kind of up to you, but hopefully you'll arrive at the correct conclusion. So this is something that appeared on August 11th. Oops. There we go. We also try to do something for a full moon. Now, the full moon is hard to see in the sky through a telescope, or at least details interesting things on it other than the light and dark areas. But this is something that the public would really, really like. And you've probably seen examples of this on the internet, of people standing in front of the moon, having it balanced on the top of their head or holding in their hand or something like that. But if you have an observing session at this time, public will like doing this with their own cameras. Encourage them to do so, and they'll get some pictures that'll always be memorable. That's for sure. Once in a while, we try to feature a constellation. This is a Delphinus, which was just a few days ago on Facebook. Again, as I've been saying, these are you can download these and distribute them to your club, put them in your newsletter, club newsletter, and so on. So it's just to get people more interested in what's going on in the night sky. This tells you all about Delphinus and how the Astronomical League's many observing programs feature something in this small but interesting constellation. A couple of days ago, we also did one on double stars again, Capricornus. If you've ever looked at a map of Capricornus, you'll notice that the northwestern corner of it is just loaded with double stars. Some of them are really easy to see. So here's what I have 1, 2, 3, 4, 5, 6. I had 8 of them there, 7 of them there, sorry. And something for you to look at during the late August and September skies. Now, as I said, today is the monthly maps appear today. So on Thursday, Friday, on Sunday, here we are in the future. We'll have the North American Nebula featured, how to find it, what you're going to see, kind of explaining a little bit what you're seeing. So again, this tries to encourage anyone really to go out and have a look at it. If you have binoculars, great. If you don't, fine. There are certain things that you can do to make it even more apparent. So this is coming up on August 25th. This will be on our Facebook page. The 27th, I'm skipping. I'll get to that in a few minutes. August 29th, the solar apex. Now, this isn't really something to see in the sky. It's just a crosshairs of where the Earth or where the sun is headed, where we're moving. And this shows you how to find that particular spot and what it is and kind of how it was arrived at. Really, an interesting story. In 1783, William Herschel was the first one who kind of came up with the idea on how to find this spot in the sky. August 29th, we'll have that. Let's jump ahead to in September, September 13th, the harvest moon. Everyone talks about it, everyone knows about it, but do you really? So this will explain it fairly well for those people who want to know more. And as I said, you can download these, you can put these in your club newsletter and so on. A little bit more, let's go just fast forward to through a few more of these. September 19th will feature the planet Saturn. Not really so much of its physical properties, but of how it appears through a telescope, what you're going to see. And this year, Saturn's rings are starting to get more edge on. Not quite. Next year, it'll be even more so. But it's not. It explains why they're approaching edge on. Again, you can download these and put them in your newsletter, share them, use them at outreach events. September 3rd and 21st. What do I got here? Oh, Dark Nebula. More of an observing program brief is what I call them, to kind of show you what the program's about and encourage you to try it. Dark Nebula requires extra dark skies to see, but they are pretty interesting if you can. Helix Nebula. We've heard about this fantastic planetary nebula, the largest in the sky. What it's all about, how you can see it a little bit better. You can see a little diagram on the lower right-hand side, giving you some tips on how to bring it out. It's not that easy to see, but once you see it, you'll be thinking, it's not that hard either. Again, you can put these in your newsletter, print them out, whatever. Now, let's talk a little bit about this. So what's on the YouTube channel? There are several items, but I'm going to focus on the one on the right with the next slide. We have a program which essentially shows how you can find things in the night sky, taking 3 minutes to do so. And this is M55, how to find M55. It's featured on August 27th, sometime next week. This is a good time of year to see M55. A few weeks ago, we did M27. A few weeks before that, M13, and so on. So we have these you can pull up and show them at your club meeting. As I said, they're only 3 minutes or so, and learn something about the night sky. Pretty cool, I think. So now you know. So what is on the League's Facebook page? We have monthly maps. We have observing activities. We have double star activities. We have every other day we try to have something on there that will show you about what you're going to see up in the night sky. So before you head outside, keep your eyes on Astronomical League Facebook. Thank you for listening to this.
Thank you, John. As you can tell, he is really amazing with graphics. He has designed all of that. I mean, yeah, he does a great job and he makes it easy. Even for a beginner, you will understand if you go and read that and look at the pictures, you're going to understand what he's talking about. But yet he also has stuff for the advanced observer too, that is interesting and looking at a variety of things. So John, thank you for the incredible work you do.
You're welcome. Well, I can't take entire credit because there are a lot of people out there who get irritated with me for sending emails, asking them questions on this and that. Are you sure this is right? How do I find this? Why should I do that? But that's why. And that's all I'm really doing and putting it all together like that. So I appreciate all the help that I've gotten. Terry knows I've gotten stuff from her, and I'm, once you say yes once, it means hey, you're fair game from then on. So thank you.
But that's fine because we know what you are putting together is spot on, and that it needs to be, especially, if we're going to put it on the website. But you do an incredible job on all the designs. So really, thank you.
Well, it's spot on, except, as I said, there's always one mistake in there, usually one typographical error someplace, and I find it like 3 days after I post it.
Well, nobody's perfect. We don't expect. I mean, yeah, that did not affect. Yeah, that's okay.
John
Sometimes that
Goss's.
happens. We all make
That's
mistakes.
that's his
So thank you,
watermark.
John.
That's his
I appreciate
watermark,
you
so
being
that it
here.
can't be copied.
Well, I'm sorry, Scott, I could not hear you if I was speaking over you.
No, that's all right. I was speaking over you. I just said that that is John Goss's watermark. These little typographical errors. So, right,
There you go. Now you have an
Well,
right.
excuse.
Those are on
thank you.
purpose.
Oh, thank you. All right. Well, our next speaker is our keynote for tonight. Let me tell you a little bit about Lou Mayo. He's a planetary scientist with over 40 years' experience supporting NASA's planetary research, space missions, and space science data centers. He was a member of both Voyager and Cassini IR Instruments team and is currently chief scientist for Gamma 1 Technologies and a professor of astronomy at Marymount University. You're a busy guy. Lou is also president of the Aries Scientific, a small not-for-profit dedicated to dedicated to astronomy education. His primary research interests have been understanding the atmosphere of Titan, Saturn's largest moon, developing radioactive transfer models of aerosols and molecular studies in Titan's atmosphere. Lou is also heavily involved in astronomy outreach and public communication. For over a decade, he led NASA's team to bring heliophysics mission science and discovery to the country, including both Venus transits and the 2017 solar eclipse across America. For NASA's space mission director, I'm sorry, director, I can't get the word. Anyway, he spearheaded astronomy education programs for Girl Scouts, amateur astronomy, university professors, and K-12 educators. And he is currently featured on the YouTube show Space Oddities, which streams every Monday at 3 p.m. EDT. Lou, thank you for being here. We greatly appreciate the talk you're about to give, and I am really looking forward to it.
Thank you very much. Thank you so much, Terry. Thank you to Scott and Terry and to the League for inviting me to be with you here today, to be with dear friends and colleagues and to do the work that I love, which is astronomy and planetary science and sharing the excitement of all of these discoveries with everyone. So thank you very much.
Thank you.
I've been asked to give a talk today on two topics. One is the exploration of Titan, and the other is exoplanets. It would seem to be rather disparate topics. However, both are central to a fundamental issue. The question, perhaps the most foundational question that our species has asked, is, are we alone? Are we alone in the universe? Are we it? And I believe the answer to that question, either way, whether we are or perhaps whether we are not alone, is both exciting, is enlightening, and also terrifying. So these are questions that really compel us to explore. And I'll be talking about two of these areas of exploration today, one in our solar system, Titan, and then going outside the solar system, talk a little bit about how we detect exoplanets. So let's get started here. Okay. Let's see, is that? There we go. There we go. Okay, let's talk a little bit about the exploration of Titan, which I believe is Earth's true sister planet. Venus just doesn't cut it, and I'll be making my case through the presentation. In 1655, Christian Huygens discovered Titan. You can see it here in a drawing that he made, Saturn in the middle, of course. A little star, I think with the A by it, I think is Titan, and then there's another star with a B by it in the lower left, which is in fact a star. So at that point, Titan became a legitimate moon satellite of Saturn. In 1907, Jose Sola discovered limb darkening. Limb darkening is the tendency of light to get progressively more obscured on the edge of a planet with an atmosphere. And so this was the first evidence that Titan had an atmosphere. And in fact, it is the only moon in the solar system that has a substantial atmosphere still today. In 1944, you'll know the name Gerard Kuiper, who carries the name of the Kuiper Belt, as well as the Kuiper Airborne Observatory. And he did spectroscopic studies of Titan and discovered methane. Well, if you're in the UK, it's methane. In the United States, it's methane in the atmosphere. Methane's important because it's a hydrocarbon. It is a biomarker. And so immediately, Titan becomes a high value target for anyone interested in the possibility for life outside the Earth. So what do we know about Titan today? Here we have a picture of Titan that was taken by the Cassini VIMS instrument, Visual and Infrared Mapping Spectrometer, where we're actually seeing through the aerosol haze down to the surface. You can see its diameter there, less than half the diameter of the Earth, relatively small surface gravity. Its density is about on the order of 2 grams per cubic centimeter. So there's a lot of water ice down below the surface. Surface pressure, 1.5 bars, in other words, 50% more atmospheric surface pressure than Earth. And interestingly, its primary constituent in the atmosphere is nitrogen, diatomic nitrogen, N2, just like the Earth. So that's all very interesting. It's starting to sound very Earth-like. Now, okay, it is kind of at a temperature of 94 Kelvin year-round, almost doesn't vary by more than a degree or two, I think, from equator to pole, because of the thick atmosphere, which is so effective at spreading heat. But beyond that, it's rather Earth-like. Here we see a comparison of Titan with some of the other moons of Saturn. It's the largest moon of Saturn and second largest moon in the solar system, just right behind Ganymede. Here we see a comparison of Titan to the terrestrial planets. Venus and Earth are about the same size. Mars is about half that, and Titan's a little less than that, but larger than Mercury. No question that if Titan were orbiting the sun and not orbiting Saturn, we would call it a planet. And well, we should. In fact, I think I should lead a protest to make Titan a planet. It's just so cool. It's such a cool little object. Well, okay, it has an atmosphere. It has methane. Ground-based observations had started to discover other hydrocarbons in the atmosphere. This made it a very, very high-profile target for planetary missions. And so we sent the Pioneer Pioneer 11 by the Saturnian system in 1979, Voyagers 1 and 2 in 1980 and 81, and in fact, Voyager 1, the rest of its mission was sacrificed in order to get very close to Titan and to get some very high spatial resolution data. 20 years later, Cassini was launched along with its Huygens probe that actually parachuted into the atmosphere of Titan, which I think is just a phenomenal engineering feat. I can't imagine 1.5 billion kilometers away, and they pegged that landing on the surface of Titan. And so we have ground-based observations and spectroscopy. We have satellite observations, spacecraft observations and spectroscopy, as well as not only from orbit and flyby, but on the surface. So we know a lot about Titan at this point, and it just gets more and more interesting. So Pioneer 11, the early robotic exploration. Here's the first image of, I'm going to tell you this, it's the first image of Titan from a spacecraft ever taken. So this, of course, is Saturn, but down below, you can see an image of Titan. And this was taken at close to 3 million kilometers from Saturn. This is the best image that Pioneer 11 was able to get of Titan. What you're seeing here, exemplified by the kind of fuzzy edge, is its atmosphere and its photochemical haze. This haze is produced by the breakup of nitrogen and methane in the upper atmosphere, and that recombines into all kinds of hydrocarbons and nitriles and produces an aerosol haze around the moon that is opaque in visible wavelengths. But as we will see, it is not opaque in certain infrared wavelengths. So in July and August 1977, 2 Voyager spacecraft were launched into the outer solar system. That's a whole different talk that I gave at Alcon. These are the flight paths of the 2 Voyager spacecraft. You'll notice that Voyager 2 went to Jupiter and Saturn and then went on to Uranus and Neptune. Voyager 1 went to Jupiter and Saturn and then out of the solar system. And again, that was so that it could get, Titan was such an important target that they were willing to sacrifice the rest of the mission to get very, very high spatial resolution data. And I was the one of the very fortunate benefactors of those data sets for a good part of my career. Here's the Voyager spacecraft. You can see when you're going to launch something into the outer solar system and spend that much time and money, you load it up with as many instruments as possible. So it has both fields and particles instruments, such as the planetary radio astronomy and the magnetometer boom and the cosmic ray detector. And it also has cameras and spectrometers that are posted on a scan platform, which can move independently, just kind of like your wrist. It can move independently of the spacecraft because those are instruments that need to be pointed. That was great because it meant that it was much easier to get the observations we needed. That was also not so great because it introduced a little pointing error into the data. Here's one of the first close-up images of Titan taken by Voyager 1. And you'll notice a couple of things. First, you might notice that the upper part of this image is darker than the lower part. This is not a solar angle byproduct. This is a consequence of wholesale movement of the atmosphere, Hadley cell movement, convective movement of the atmosphere between one hemisphere and the other. And so we're actually seeing a particle size and a particle composition difference in the 2 hemispheres of Titan. This happens because Titan's a very slow rotator, being tidally locked to Saturn, and so it doesn't have so many Hadley cells. Earth has, I think, 3. They're not exactly called Hadley cells, but they are in fact convective Hadley cells, 3 between equator and pole. And Jupiter is a much faster rotator. It has, I think, 6 between equator and pole. So Titan has 1. You'll notice that in the upper part of this image, there's some dark features. That is the North Polar Hood. This is an area where, in this case, in the winter time on Titan, this is shaded. Titan has axial inclination, and so this area is shadowed, and there's a buildup of particulates in the atmosphere at that time that creates this much more opaque and much darker kind of photochemical haze. This is an example of some of the data we got from Voyager 1. On the right-hand side here, you see the geometry of the SATAT link that was able to scan the IRIS, the infrared interferometer spectrometer, the instrument that retrieved infrared spectra of Titan. We scan from off the planet down onto the limb and then further down onto the surface. And so we were able to get, if you look at the left-hand side, infrared spectra showing molecular species as well as regions of aerosol opacity. And what makes Titan, one of the things that makes Titan so exciting and so interesting is that this very simple photochemical model of breaking up methane and nitrogen, these resulting molecules and atoms come together in a variety, just an enormous variety of other molecules, some of them regarded as building blocks of life here on Earth. So Titan is largely regarded as a kind of an early Earth, perhaps a prebiotic atmosphere. Well, what do we look for? We rely on the photochemists here on Earth to create the models for us that tell us what kinds of molecular species we should be looking for. On the upper left, we see the methane and how it gets disassociated and recombined into its various components. And down below, we see nitrogen and the nitriles that exist in Titan's atmosphere. You'll notice hydrogen cyanide, HCN, which is an amino acid building block. Well, for a long time, we didn't have any high resolution images of the surface. These are two sets of images. On the top, you see images in the infrared of the surface of Titan. This is from the Canada-French-Hawaii telescope on Mauna Kea. And if you look between methane absorption features between 1 and 2 microns, you can see down to the surface. Down below, the Hubble Space Telescope, largely regarded as a visual and ultraviolet instrument, but it does reach into the near infrared, and it is able to look between some of those bands and see down to the surface. So at this point in time, all we had were indications. There were bright markings, there were dark markings. We didn't know what they were. Were they mountaintops? Were they lakes? We really didn't know, but this is the kind of information that we had before Cassini, actually. Now, for you amateur astronomers out there, you might be interested to know that although it is a challenge, if you have a large enough aperture and enough patience and you can stack enough images, it is possible to get some spatial resolution of Titan from 1.5 billion kilometers away. Titan has a angular diameter of 0.7 arc seconds. So it's very, very small. I should talk with Aaron Clevenson. Perhaps this already exists, but I would love to see an observing challenge where amateur astronomers try to resolve the disk of Titan. It's a challenge, but I understand that it can be done in part. On the left, you see one of those images magnified greatly, which perhaps doesn't show much in the way of features. Of course, you don't see much even close up because of the photochemical haze. And on the right-hand side, we see the Cassini infrared, the Cassini infrared imaging subsystem image of Titan. So there's a challenge for you if you choose to accept it. There are some published papers in peer-reviewed journals regarding the observations from amateur astronomers of Titan photometry as well as spectroscopy. So I can provide these references for you for anyone who's interested. I mentioned earlier that by looking through the absorption lines of methane between 1 and 2 microns roughly, we can see to the surface. And the VIMS instrument on Cassini, the Visual and Infrared Mapping Spectrometer, was designed to be able to do this. Voyager, a little complicated, but Voyager essentially did not see the surface of Titan. However, the infrared instrument, which had a rather large 1/4 degree field of view, in fact, did see the surface, and there's at least one paper talking about some very low resolution images of the surface from Voyager. But Cassini was built the Cassini-Venz instrument was built to see the surface of Titan. So Cassini was launched in 1997 along with its Huygens probe. Here you see one of those beautiful VIMS instruments seeing through the haze. Dark areas turns out, are lakes, hydrocarbon lakes. You can see lighter areas, which are surface features. And as we will see, there are even methane clouds in the atmosphere of Titan. So there's just a picture of the launch back in 1997. And here's an artist's conception of the Huygens probe, which was sent to the surface, parachuted to the surface of Titan. Remember, Titan's atmosphere is very thick, very extended, and so parachutes work pretty well. The Huygens probe had a downward pointing camera. Here are a couple of images as the probe was parachuting down to the surface. You can clearly see what we used to call fluvial channels. These are rivers that were cut by liquid hydrocarbons on the surface. So I mentioned that there are methane clouds in the atmosphere of Titan. These clouds have methane particles in them that eventually congeal and come together and drop out as methane rain, as well as other hydrocarbons like ethane and acetylene and diacetylene and hydrogen cyanide and many others, and they fall to the surface. Many of them remain on the surface, some make their way below the surface. Methane evaporates back up into clouds, and that cycle continues. So instead of a water cycle on Titan, you have a methane cycle resulting in the lakes and flow channels that we see here. In the bottom right-hand image, you can see not only the flow channels and a kind of a grayish lake of hydrocarbons there, but some lighter features, which are in fact tropospheric methane clouds. And Voyager Iris provided some of the fundamental data that allowed us to speculate about methane clouds and methane supersaturation in the atmosphere of Titan. Here we have pictures from the surface that the Huygens probe made. You're seeing liquids. The smooth areas are hydrocarbon liquids. The objects that appear like rocks, and you can see how they're measured here, and are probably water ice coated with tholins, coated with these very complex hydrocarbons and nitriles that rain out over the surface of Titan. This is Titan from orbit. This image has been pretty strongly color coded, image processed to bring out features. But the blue areas are, this is, I think, is the South Polar region from Cassini. The blue areas are lakes, are hydrocarbon lakes in the South Polar region of Titan. So here again, the VIMS instrument, a full global image of Titan with its darker areas of hydrocarbon and nitrile lakes, its polar regions. We talked about North Polar Hood, which is a seasonal effect. And in fact, we see a South Polar Hood 15 years later, which is a half of a Titan year. And we can see some very, very bright white features, and these again are tropospheric methane clouds that exist below the 40-kilometer tropopause in Titan's atmosphere. Here's some other data that we got from Cassini. This is a radio occultation experiment. So you fly the spacecraft behind the moon, and you send a radar signal, send a radio signal through the atmosphere, scanning down through the atmosphere. And that signal gets attenuated by the time it gets to Earth. And that attenuation gives you a quantity of T over M, the temperature at the height that you're looking in the atmosphere over the mean molecular weight in that part of the atmosphere. So therefore, if you know the temperature, you can get the composition. If you know the composition, you can get the temperature. And so we were able to form in the lower right here thermal profiles of the atmosphere of Titan. You see the temperature decreasing in the troposphere, just like on Earth it does. And then it turns over at what's called the tropopause, just like on Earth, and then increases with height in the stratosphere. Just some examples of the spectra that we got from the Cassini, on top the Voyager infrared instrument, and on bottom the Cassini infrared instrument. That was called SEERS, Composite Infrared Spectrometer. Two regions in Titan's atmosphere. And one thing that you can see is that the Cassini SEERS instrument had a much higher spectral resolution than the Voyager IRIS did. It also had 3 focal planes, as opposed to 1 focal plane that IRIS had. But in both cases, we're able to identify really exciting soup of chemicals in the atmosphere, molecules, if you will. And from all that, we're able to build models of the atmosphere with methane and nitrogen photodisassociation high up, producing the aerosol haze. We were able to model this data and discovered the presence of condensate layer, which scattered light somewhere around 80 to 90 kilometers, as I remember, and then water, some ices and some methane clouds, rain, and some flow channels and this kind of thing. So from these rather boring spectra and other types of data, we're able to find out a great deal about the physical environment of Titan by understanding how the physics comes together with the observations. We can even start to build models of the internal Titan. We know as we fly by Titan that the spacecraft's orientation is bent a little bit by the gravity of Titan. That's how we know that its bulk density is around 2 grams per cubic centimeter. And so we can start to build models from what we know of the physics of the outer solar system, where there might be methane oceans, perhaps even water oceans under the surface. I just thought this was a beautiful image. That's the only reason I'm showing you this. This is an image of the limb of Titan, a limb scan, so to speak. And you can see that the atmosphere is somewhat segmented and detached. And this was a feature that was noticed both from Voyager and from Cassini. And then this picture is super cool. This is the sunlight glinting off a hydrocarbon lake on the surface of Titan. And the imaging subsystem was able to snap this picture. So I just thought that, that was so cool. Well, what do we have now? Voyager has done its thing. Cassini has done its thing. We have, again, Hubble Space Telescope images with Wide Field Planetary Camera 2 of the surface of Titan, as we had before. So here we kind of know what those features are, and we can watch them as they rotate around Titan. So here are the benefits of having Earth-based or Earth-orbiting imaging is that you can do very long baseline studies. And we have James Webb Space Telescope, which has more spatial resolution and can see further out in the infrared, looking again here through the haze, seeing surface features and cloud features in the atmosphere of Titan. What's next? Well, the Johns Hopkins Applied Physics Laboratory is building now the Dragonfly mission. This is our next exploration of Titan. This will be a nuclear-powered drone that will parachute into the atmosphere of Titan, land on the surface, look around, take off, look for something interesting, land, take measurements, images, spectroscopy, local physical environments like pressure, winds, temperature, and so on. And so this is being developed now at the Johns Hopkins Physics Laboratories in Baltimore, Maryland. And I think I have, this is just a little kind of a diagram of the orbit, the trajectory of the spacecraft with a few gravity assists, and then arrival at Titan in 2034, and then kind of a picture of how it's going to parachute into the atmosphere of Titan. Here, however, is an animation of that landing. Here we go. The copter has 8 rotors. Whoops, sorry about that. 2 on each axis. It's nuclear powered because at Saturn you get 10% of the light, 1%, see, 10 times further, 1% of the light that you do at Earth, and about 10% of that makes it to the surface of Titan. So you're not going to power this with solar cells. So here it lands, it goes off, it looks around for interesting things to discover, radios back, so to speak, to Earth, and then is able to land and take more measurements. Well, what's the future of Titan? Very interesting paper by Ralph Lorenz, Jonathan Lenine, Chris McKay in 1997 speculated about Titan under a red giant sun. Right now, the photochemical haze around Titan is being produced by ultraviolet radiation from the sun. When the sun becomes red giant, its ultraviolet flux is going to drop precipitously, and that's going to clear up the atmosphere. The sun is going to be very large, and so it's going to have a lot of surface area to pump out photons. And that's going to warm Titan up. The water that exists on the surface now, which is frozen out like steel, will be able to be liquid on the surface, and the hydrocarbons will go back into gaseous phase. And so there's a real possibility that in the distant future, we could have lakes of water on Titan, and it might be a very nice place to live. So any of you out there who are interested in some waterfront property on Titan, come see me after the talk. I've got some good deals for you. Okay, so in summary, is Titan really Earth's sister planet? Well, Earth has poles and polar processes and seasons. Earth has lakes and rivers and volcanoes. We know that, by the way, now that Titan is volcanically active. Earth has water and a nitrogen atmosphere, clouds, has precipitation, has a smog, and symbiotic chemistry. Well, guess what? So does Titan. So that's my case for Titan as Earth's true sister planet. So that's Titan, one of the high value targets for looking for life in the solar system, along with Mars, Enceladus, and Europa. I'd say are the other 3 big ones. By the way, Europa Clipper will launch in October. Don't miss that launch. But let's go outside the solar system. And let's talk a little bit about exoplanets. The thought 50 years ago that we could even detect exoplanets, planets around other stars, was unthinkable. One of my heroes, actually, is Giordano Bruno. He thought kind of the other way about 2,000 years ago. No, I'm sorry, not 2000, back in the 1600s. And Bruno thought, well, those stars are probably suns and they probably have planets around them and they might have life. And he was kind of a loose cannon in that way, and so they burned him at the stake. So that's his story. He did not recant his beliefs. And so I dress up as him on Halloween sometimes to honor him. Giordano Bruno. But let's talk about exoplanets. Now, there are a number of ways to detect planets around other stars. I'm showing you 7 here, and we're going to go over these rather quickly. And it turns out that by using these methods, predominantly the transit detection method, but not solely, we have discovered over 5,000 planets around other stars, and we're very close to 6,000. And then I have a cool video to kind of show you how those discoveries progressed over time that we'll see at the end. So, pulsar timing. Turns out that a planet orbiting a pulsar will change the period of that pulsar's pulsing just enough to notice. And so we don't have many observations of this, but we do have some where we can identify a planet orbiting a pulsar, rather a kind of a dead a neutron star, right? And can identify that there's a planet orbiting that pulsar. There are 2 other ways to do it. What you're seeing here is some kind of fun animation that shows a planet in the upper left orbiting a star. The planet pulls on the star pulls on the planet, and they orbit some sort of a barycenter. That barycenter might be buried inside the star, or it might be outside the star, but in either event, both of them orbit. And so as we look at this, let's go to the lower left. As we look at this in the sky, we can see the planet and, more importantly, the star seem to move back and forth. This is called the detection of planets around other stars. Noticing how the star wiggles back and forth is called astrometry. And that has produced some detections. It's quite sensitive, though, regarding distance. The further away the star is, the less of an angular shift it'll appear to have. So you can only use this for planets around other stars in a certain radius from the Earth. On the right-hand side, we see that as the planet pulls on the star, as it orbits the star, the light from that star shifts due to the Doppler effect, because the star is moving both towards us and away from us. And we can detect that motion spectroscopically. And from that, we can deduce that there's a planet orbiting that star, and we can get its orbital period and some other physical parameters. This is not as sensitive to distance. And so this is a much more effective way of detecting planets around other stars. And here, 51 Pegasi was detected using the radial detection method. And this is actual data from 51 Pegasi, or if you're an astronomer and you want to sound cool at a party, you just say 51 Peg, and everybody understands what that is. And this was one of the first detections of a planet orbiting a main sequence star, and this is the radial detection of the Doppler shift in its spectrum. The most productive way so far that we've detected planets around other stars is from the transit detection method. This means that the planet is orbiting roughly in the plane that we see from Earth. And as the planet moves in front of the star, we see it blocking out a little bit of the star's light. And then it recovers. And then if it happens again periodically, we know there's a planet orbiting that star. This tends to be most sensitive for larger planets, where you have a bigger dip in the light curve, and planets that are orbiting fairly close to their star, so that the inclination of the orbit is not, the detection is not as sensitive to the inclination of the orbit. We've sent 2 spacecraft, Kepler and TESS, transiting extrasolar survey satellite, to observe and detect extrasolar planets using the transit detection method. So that plus ground-based observations have resulted in the majority of the detections that we've made to date. Here's what it looks like if you have multiple planets orbiting another star roughly in the plane that we see from Earth. And we can see periodic dropouts of different sizes, different angles based on whether the planet has an atmosphere or not. the dropout will have a different angle to it. And so we can detect multiple planetary systems this way as well. Then there are spectroscopic detections. We have identified atmospheres of planets and the constituents in those atmospheres using spectroscopy. And the way that happens is the star emits light. As the planet moves in front of the star, that light moves through the cooler atmosphere of the star, okay? And because the atmosphere of the planet, see, I'm not saying that right. Let me say that again. The star emits light. That light travels through the cooler atmosphere of the planet. And because that atmosphere is cooler than the star, you'll see those emissions, the molecular and atomic identifications in absorption. And we can see that on the right-hand side of this graph, okay? So when the planet moves in front of the star, we can see a very tiny spectral features from the atmosphere of the planet. And with better technology, better detectors, better telescopes, we are actually able to do that now. And here's one of those detections. This is actually from the James Webb Space Telescope. And if you'll just bear with me, because what we really want to do is take this and flip it, right, on its head. And then if you can flip it on its head, these regions that appear to be high are in fact in absorption. So this is identification of water vapor absorption lines in the atmosphere of an exoplanet from James Webb. We can also actually see these planets around other stars. This is the first image that was taken of a planet around another star, very descriptive 2M1207b. This is the way you identify planets. The very first planet you see around another star, it gets the letter B. The next planet that you discover is the letter C, and so on. So the first detection visually of a planet around another star, and this is a rather large super Jupiter, was in 2004. And here we have data taken over many years of 4 planets orbiting another star. The instrument that observed this had to put a mask over the star so that the brightness of the star was occulted. And so what you can see here are 4 planets actually orbiting. This is a collection of data from, let's see, from 7 years, I think. And we can detect planets around other stars in very unique geometries through gravitational microlensing. All right, we know from general relativity that massive objects distort space and therefore bend light. And we can see that effect as in this case, the star with the planet orbiting it is closer to us than the distant star. When that planetary system comes in front of the distant star, you see an increase in the light curve. And when the planet is involved in that, you actually see a second peak in the light curve. And that is from gravitational microlensing, identifying an exoplanet. So this is from July 25th of this year. Just a kind of a graphic showing which techniques have been most effective in detecting extrasolar planets. We see some techniques I didn't talk about here: orbital brightness, modulation, disk kinematics. But you can see that by far the most productive has been transit detection method. And the second, and remember it's not so sensitive to orbital inclination or distance, is radial velocity method. And then we have other methods that have been used but have made fewer detections. If you all are interested in this kind of thing, you can go to the NASA Exoplanet Archive. They have, and I just updated this yesterday. So as of yesterday, there are 5,747 confirmed planets around other stars. 545 of those are from the Transiting Extrasolar Survey satellite, and we have over 7,000 candidates from tests that are being observed with other methods from the ground, and presumably some of those will go into increasing the number of confirmed planets that we have. But the NASA Exoplanet Archive has more data than you can imagine, and if you're interested in exoplanets, it's a great resource. The other great resource that I would suggest is Eyes on Exoplanets. It's a software that came out of Jet Propulsion Laboratory, Eyes on Exoplanets. And you can no, you don't download it anymore. You use it from the web, and you can see the geometry and the positioning and look at the 3D interactive models of every exoplanet that has been discovered. Here's a kind of a cool animation showing the year that the planet was discovered, the exoplanet, and how many, kind of a accumulation of the number that we have found up through, I think, 2022, maybe? Yeah, so I'll let it play again. Initially, we're just discovering a couple here and there, and then all of a sudden, whoops, all of a sudden, the numbers just take off, and we're detecting, you know, almost new planets every day. I'd like to conclude with just two references for some outreach efforts, some astronomy communication efforts that I'm involved with. One is the NASA Solar STEAM, which is a NASA grant out of the Heliophysics Division at NASA headquarters. And if you're interested in that, we have a YouTube channel at NASA Solar STEAM, and it's all things and everything's heliophysics. But we of course include a lot of planetary science, and there is heliophysics to be found in exoplanet surveys as well. So if you're interested in that kind of thing, especially Parker-Smith probe, eclipses, things of that nature, solar STEAM. And the last is the YouTube show that Terry mentioned. It turns out, sorry, it's every Tuesday now, every Tuesday at 8 p.m. in the UK or 3 p.m. on the East Coast of the United States. This is live astronomy with amateur and professional astronomers. And we talk about the latest findings, the latest launches, the latest discoveries. And we have challenges and quizzes, all kinds of things. So you're interested in that, Space Oddities on YouTube. And I will conclude there and take questions.
Well, Scott's checking. I have one comment. I can't believe everything that's going on in exoplanets. I mean, there is so much happening and so many new discoveries. But what I really like is that dragonfly. That sounds like an incredible way to hop around the planet. How will dragonfly decide what is worthy of it making a trip or doing to stop at that object?
Well, we have maps of the surface of Titan now. So we have a kind of general sense of what the landscape looks like. But Dragonfly is going to see it up close, and so we can provide kind of general direction. Of course, it has a lot of smarts in it, because at 1.5 billion kilometers, we can't use a joystick to power this thing. So it has a lot of artificial intelligence and a lot of pre-programmed methods for figuring that out on its own. And then it will come back, land, send that information back to Earth, and scientists will evaluate that, and then we'll send the next set of commands to Dragonfly.
That's pretty amazing. Scott, do you have anything over there?
Yeah, we have a question here from Cynthil Nagapan. He wants to know, how does a young person get involved in any of the programs you discussed? Maybe from the aspect of like internship or something.
That NASA has a lot of internships that you can find just by Googling it. the NASA Office of Education, and each field center's offices of education, Goddard Space Flight Center, Jet Propulsion Laboratory, Ames Research Center, Langley Research Center, and all of there are 10 research centers. So both NASA headquarters and the individual field centers have very dynamic outreach and internship programs. So just check those out. They're readily available. They're easy to find, and they are there for high school students. They're there for college students, and give it a shot.
Okay. And a question I have is, Lou, what do you think are the most promising signs or conditions on Titan that might support life?
Well, of course, that's the great question. Let me start answering that this way. The more we explore the Earth, the more diversity of life we find. We now know of a category of life that can exist under very extreme environments. They're called extremophiles. They can exist in highly acidic lakes. They can exist on the radioactive surfaces inside nuclear power plants. Some of them can exist in space without oxygen and in just wild ranges of temperatures. So, or at the bottom of the ocean in hydrothermal vents. We know that life wants to exist. Anyone who has ever seen a weed or a flower growing out of a crack in the pavement knows that life wants to exist. Okay. It was once believed that what you need to look for is a planet in the Goldilocks zone. This is the region, the distance from a star where liquid water could exist on the surface of that planet in liquid form. I think that's clearly too restrictive now. We're discovering subsurface oceans on a number of solar system bodies. So I'm just answering your question by beginning to say the survivability and the diversity of life may be even greater than we know it today. Having said that, from what we know of life on Earth, I would say that subsurface water ocean on Titan could be a place where life could evolve. The question there is, can you get nutrients down below the surface, perhaps through meteoric impacts? Perhaps there are, Titan does have slightly eccentric orbits. There is some tidal friction. Perhaps there are underground or ocean surface vents that can provide nutrients. So I would say that's our best chance of finding life on Titan right now.
Okay. Thank you. Thank you.
All right. Well, Lou, thank you. That was amazing. Anytime you want to come back, you just let me know. There's so much going on. I mean, there is so much to learn that really it's nice to have somebody that is inside that can tell us some of the projects that are going on and give us a little more information. So thank you for that. I really appreciate it. I know you're on the road, you're not home. So I know you took some time out to do this. Thank
Thanks
you
so much.
very much.
Really appreciate being able to be with you today.
We appreciate you too. So, all right. Thank you all, everybody out there that tuned in to watch us. We will be back September 20th, and we'll have Scott Harrington with us. We don't know just yet what his topic will be, but as soon as we do, we'll let you know. So please make sure to write down September 20th at 7 o'clock Eastern Time and join us again. So thank you all again. It's so nice to have you there every Friday on a Friday night. And Scott, I'm going to turn it over to you to close it up.
Okay, all right. I'll be happy to do that. Actually, sad to do that because I think that there's So many other intriguing questions that we could be asking Lou at this time. So, but really wonderful. And I want to thank you, Terry, for bringing on all these amazing people. So
It's my pleasure. It's so great to hear all these guys. Everything we've had so many men and women on here that have just been incredible.
that's
And
right.
Lou definitely is one of them, and so is David.
Yes.
I often count myself as a man or woman, so thank you, Terry.
Okay, you're welcome.
Very good. Very good. Okay. All right. Well, thank you again, Lou and Terry. And we will end this program with a little NASA video about, I think it's about Titan. So, which you might want to stay tuned for. So here we go.
One of the most shocking discoveries of the past 10 years is how much the landscape of Saturn's moon Titan resembles Earth. Like our own blue planet, the surface of Titan is dotted with lakes and seas. It has river channels, islands, mud, rain clouds, and maybe even rainbows. The giant moon is undeniably wet. The water on Titan is not, however, H2O. With the surface temperature dipping 290 degrees Fahrenheit below zero, Titan is far too cold for liquid water. Instead, researchers believe the fluid that sculpts Titan is an unknown mixture of methane, ethane, and other hard-to-freeze hydrocarbons. The idea that Titan is a wet world with its own alien waters is widely accepted by planetary scientists. Nothing else can account for the observations. NASA's Cassini spacecraft has flown by Titan more than 90 times since 2004, pinging the moon with radar and mapping its lakes and seas. ESA's Huygens probe parachuted to the surface of Titan in 2005, descending through humid clouds and actually landing in moist soil. Yet something has been bothering Alex Hayes, a planetary scientist on the Cassini radar team at Cornell University. If Titan is really so wet, he wonders, where are all the waves? Here on Earth, bodies of water are rarely still. Breezes blowing across the surface cause waves to ripple and break. Raindrops striking sea surfaces also provide some roughness. Yet on Titan, the lakes are eerily smooth, with no discernible wave action down to the millimeter scale, according to radar data from Cassini. We know there is wind on Titan, says Hayes. The moon's magnificent sand dunes prove it. Add to that the low gravity of Titan, only 1/7 that of Earth, which offers so little resistance to wave motion, and you have a real puzzle. Researchers have toyed with several explanations. Perhaps the lakes are frozen. Hayes thinks that is unlikely, however, because we see evidence of rainfall and surface temperatures well above the melting point of methane. Or maybe the lakes are covered with a tar-like substance that damps wave motion. We can't yet rule that out, he adds. The answer might be found in the results of a study Hayes and colleagues published in the July 2013 online edition of the journal Icarus. Taking into account the gravity of Titan, the low viscosity of liquid hydrocarbons, the density of Titan's atmosphere, and other factors, they calculated how fast wind on Titan would have to blow to stir up waves. A breeze of 1 to 2 miles per hour should do the trick. This suggests a third possibility. The winds just haven't been blowing hard enough. Since Cassini reached Saturn in 2004, Titan's northern hemisphere, where most of the lakes are located, has been locked in a grip of winter. Cold, heavy air barely stirs and seldom reaches the threshold for wave making. But now the seasons are changing. In August 2009, the sun crossed Titan's equator heading north. Summer is coming, bringing light, heat, and wind to Titan's lake country. According to climate models, winds will pick up as we approach the solstice in 2017 and should be strong enough for waves, he says. If waves appear, Cassini should be able to detect them. Radar reflections from wavy lake surfaces can tell researchers a great deal. Wave dimensions, for instance, may reveal the viscosity of the underlying fluid and thus its chemical composition. Hayes is excited about bringing oceanography to another world. All we need now, he says, are some rough seas.